Hi, geometry students. If you're looking in the book at Menelaus and Ceva, I think it has a well-written explanation because I wrote it. But I always get questions about the Menelaus and Ceva dance. How does it actually work? Both of them have a sequence of fractions times each other that equals 1. But how are we to tell? What are the right segments? What are the right letters to write in the places? Well, it's a very simple dance that goes vertex, point, point, vertex, vertex, point, point, vertex. So that's the dance. It just does that for the names of the letters. To get the letters in the right place, that's how you name them. Each fraction is vertex point divided by point vertex. Now let's take a look at this vertex A, point D, vertex B. See B? Point B, vertex, vertex B, point E, vertex C. Vertex C, point F, vertex A. So you come back around to A. And those lengths have to multiply out to be a fraction. The fractions have to multiply out to be 1. So let's take a look at a typical example. I've got a triangle here with very carefully measured distances as marked. And one of the extended segments, this little guy here, CF, is called X. So the typical question is solve for X. Well, these 3 points, D, E, F, you can see are on a line. So Menelaus' theorem says then these fractions must multiply to give you 1. Just write out the numbers in the right spot. So I've got the numbers here. You can pause and look at the calculation there. But that gives me that X is 32/17, slightly less than 2. Now, one of the things that can happen with Menelaus is the extended sides can either be 1 extended side or 3 extended sides. You can't do it with 2 extended sides. Menelaus proved that. But if you notice, this layout, even though it looks different from the one up here, the fractions work out exactly the same because you do vertex, point, point, vertex. Vertex, point, point, vertex. Vertex, point, point, vertex as you're setting up the same exact fractions that time. I was kind of careful to get the labeling that way so I wouldn't have to write it twice. Now let's look at the same dance in a different position. You've got Cevians. A Cevian is a segment that starts at a vertex and goes to the side opposite in a triangle. So these red segments are Cevians. So a triangle has many Cevians. This point E doesn't have to be anything special. Any segment that runs from a vertex to the opposite side is a Cevian. Now, so these Cevians can be all over the place. They just have to be inside the triangle. So the Cevians are concurrent, which means they meet in one point like they do in this picture. They would all meet in this one single place. If and only if. And look at this. It is vertex, point, point, vertex, vertex, point, point, vertex, vertex, point, point, vertex, just like before. Same kind of structure in the product, and it equals 1. However, the pieces now just lie on the original triangle ABC. If you look back over here, there was somebody that was off the original triangle, or in this case, 3 pieces that are on extended sides off the original triangle. These guys are always on the original triangle. So let's take a look at this last little bit here. So a typical use would be prove these Cevians in this picture are concurrent. And you can't just say they look concurrent. That's not a proof. So you say, well, Ceva's theorem says if this product of fractions comes out to be 1, then the Cevians must be concurrent. So AF is X, FB is 2Y, BD is Y, DC is 4, EC, CE in this case, is 8, and then EA is X. And if you notice, the X's cancel, the Y's cancel, 2 times 4 is 8. Everything cancels out by division, you get a 1. And Ceva says then these Cevians are concurrent. Which means, if you were building this triangle with actual numbers, you'd only have to pick a number for X and a number for Y. And as long as the triangle inequality is satisfied, you're okay. And triangle inequality says that any 2 sides have to add up to be more than the 3rd side, because it's possible to assign numbers so that 2 sides are too big. Let me just show you like this. If I had 1, 2, 3, 4, 5, 6. If I did that, that satisfies the triangle inequality because 5 plus 7 is bigger than 9. 7 plus 9 is bigger than 5. But if I do this, 1, 2, 3, 4, 5, 6, that'd be no such triangle because 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 3 is 10. 5 plus 6 is 11. This side, this triangle is impossible. Also, Ceva's theorem wouldn't, everything wouldn't cancel anyway. But I'm just showing you, you can't just choose whatever lengths you want for the sides. So that's the Menelaus-Ceva dance. Good luck with that. Play this video over again if you want. Now I've got one more thing. And this is mentioned in the book, but not emphasized because it would take another 3 pages. But here's what's going on. When you're doing the incircle construction, you use 2 angle bisectors. So here's what I did. I started with red segment AB, and I'm thinking, yeah, I think you can see there's arcs meeting up here at C that make the 2 green sides the same size as the red side. So I've constructed these 2 little moves here, show you how to construct an equilateral triangle. A very easy thing to do. Now, the purple segments are angle bisectors because to get this mark, I put the point of my compass here and made an arc. I put the point of my compass here and made an arc. So that means that I can also use the this point here, this distance, CB is equal to CA. So from the vertex A, point B and point A are equidistant from C. So I can put the point of my compass here and make an arc there. I can put the point of my compass here and make an arc there, and they meet at the place where I would get the angle bisector. I don't have to make new arcs. But you know, you can make new arcs, you're still going to get the same angle bisector. I did the same trick here. I used these 2 points for the point of my compass, made arcs up here. Here's the 2 angle bisectors, and because this is an equilateral triangle, this angle bisector is also an altitude. So that's a right angle right there, which means I know from the in-center eye to here, that's a useful radius. So I drew the incircle because I knew the radius. Now compare that to a non-isosceles triangle. So this time, I on purpose made the 3 sides different lengths, and look what I had to do. I still did the 2 angle bisectors like before. You can see the extra marks for them because I had to make extra marks. I didn't have symmetry all around to take advantage of. So I made extra marks here and here for this angle bisector. I made extra marks here and here for the perpendicular. So after I get some angle bisectors, I get these 2 angle bisectors that are in purple. I get the in-center. I still have to do a perpendicular to a side to get the radius right. So that's what I put the point of the compass here. I made marks on this side, put the point of the compass in each of those places, made marks down here. That's perpendicular. I constructed the perpendicular through a point not on a line. That gives me this has to be a radius because the radius is perpendicular to the tangent at the point of tangency. So I got the radius right. These are important ideas because I get, you know, it'll be on, say, a test, construct the incircle, and there'll be this triangle lying there. And the kids will do the angle bisector right, and they'll forget to do the perpendicular for the radius. Since you can't just eyeball it. You can never, in a construction, just put the pencil of your compass in a point by guesswork unless it's right at the beginning, if it's some size that doesn't matter. If it's a size that matters, you have to know where to put the point and the pencil of your compass. Okay, gang, keep in touch. Hit that wiki. Bye-bye.